And welcome back. As we continue our cosmic journey, let's go ahead and take a small detour to discuss the laws of planetary motion. So in order for us to have an understanding of the laws of planetary motion, we need to do a little bit of history. So let's first by talking about Tycho Brahe. Tycho Brahe was kind of the last, maybe greatest pre-telescopic observer in Europe, because after this point we started having more instruments that would really kind of lend themselves to having more ability to view deeper in space. Now, Brahe made a continuous record of the positions of the Sun, the Moon, and planets for almost 20 years. His extensive and precise observations enabled him to note that the positions of planets varied from those given in published tables. This data that he gathered actually was extremely valuable, but Brahe didn't have the ability to really analyze the data or develop a better model based upon what he was observing. Now, in the year before his death, Brahe found a most able young mathematician, Johannes Kepler, to help him in analyzing his extensive planetary data. So Johannes Kepler, of course, is a very famous mathematician, but one of the things that he brought to the table is that he had learned first of the Copernican system, and by extension of that, the heliocentric hypothesis. So he wasn't as married to the geocentric model as some of his contemporaries may have been. Now, Kepler served as an assistant to Brahe, as we already mentioned, who sent him about to work finding a satisfactory theory of planetary motion that was compatible with his data. Now, Brahe was at first very reluctant to give Kepler much of the material because he feared, well, Kepler is going to steal all my glory. It wasn't until after Brahe's death in 1961 did Kepler get full possession of those priceless records, because remember, it was 20 years of collected data and observations. Now, that information occupied most of Kepler's time for more than 20 years, because there was, again, 20 years of data for him to go through. So he's got to spend time to catalog and analyze all of it. Now, through his analysis of the various motions of planets, Kepler actually devised a series of principles, which are now known as Kepler's three laws, which describe the behavior of planets based on their paths through space. The first thing, of course, has to refer to the shape of the orbits. Now, the path of an object through space we just simply refer to as its orbit. Kepler initially assumed that the orbits of planets were circles, because this came back from ancient Greek times where they believed the circle was this perfect thing, and they said, well, the planets must be defined by the gods, and so they have to be these circles. However, doing this adherence to circles did not allow him to find the orbits that were consistent with Brahe's observations. So working specifically with the data for Mars, he eventually discovered that the orbit that a planet had around our sun was somewhat of a flattened circle, or an ellipse. So if we start talking about the difference between a circle and an ellipse here, in a circle, the center is a very special point, because, everything in a circle is going to have the same distance from that center. Whether you're at the top of the circle, bottom circle, left, right, wherever you are on that outside of the circle, it's going to have the same distance. However, if we look at an ellipse, the sum of the distance from any two special points inside the ellipse to any point in the ellipse is always the same. Now, these 2 points on the ellipse are focuses, or foci, if we were talking plural here. And Kepler generalized that the findings in his first law and said, hey, all the orbits of the planets are actually ellipses. And then, of course, we have his second law, which is the law of equal areas. Kepler's second law deals with the speed at which each planet moves along its ellipse, also known as an orbital speed. Now, working with Brahe's observations of Mars, Kepler discovered that the planet speeds up as it moves close to the Sun and slows down as it pulls away from the Sun. When Mars is close to the Sun, position number 1 here and 2, so these 2 points, the elastic line does not stretch as much and the planet moves pretty rapidly. Farther from the Sun, though, when it gets to the other side of its orbit, positions 3 and 4 here, the line stretches a lot, so the planet does not move so fast. And with Kepler's third law, you have to understand the first 2 laws of planetary motion are describing mostly the shape of the orbit and allows us to calculate the speed of its motion at any point. But the third law really kind of came back because Kepler said, I want to know why the orbits of planets were spaced as they are, and I wonder if I can find a mathematical pattern in their movements. For many years, he worked to discover the mathematical relationships governing planetary spacing and the time each planet took to go around the Sun. So this meant he had to do a little bit of calculations. Kepler discovered a basic relation to the planet's orbits to their relative distances from the Sun. So a planet's orbital period, p, is the time it takes a planet to travel once around the Sun. A planet's semi-major axis, a, is equal to its average distance from the Sun. So he said, well, this relationship says that a planet's orbital speed squared is proportional to the semi-major axis of its orbit cubed. So we can rewrite this as p squared equals a cubed. And when we think about p being measured in years and a is expressed in astronomical units, the two sides of the formula actually become proportional and equal. Kepler's third law applies to all objects orbiting the Sun, including Earth, and actually provides a means for calculating their relative distances from the Sun the time they take to orbit. So let's go ahead and summarize those three laws because it seemed very technical here. So the first law simply says each planet moves around the Sun in an orbit that is an ellipse, with the Sun at one focus of the ellipse. Kepler's second law says that there is a straight line joining a planet and the Sun that sweeps out in equal areas in space at equal intervals of time. And Kepler's third law says the square of a planet's orbital period is directly proportional to the cube of the semi-major axis of its orbit. Kepler's laws in this case, though, are purely descriptive, and you'll notice they don't actually help us understand what forces of nature constrain the planets to follow the set rules, though that side of things would actually have to wait until another mathematician came along called Isaac Newton, who could actually then develop the math that would be needed to really work out what Kepler had observed and determined here.